Okay, let's unpack this glass. It's absolutely everywhere, right? Your windows, your phone screen. A simple drinking glass,
Ubiquitous.
totally. It's transparent, familiar almost, mundane. But have you ever stopped to truly consider why it's transparent?
Hmm.
It seems like such a basic property, something we just take for granted, but this seemingly simple question actually stumped the scientific community for a very long time.
Indeed it did. What we're diving into today is the truly unexpected physics of electrons in non-crystalline materials, what we call amorphous materials, with a special focus on glass.
Right.
And our guide for this fascinating journey is none other than Nobel laureate Nevill Mott, drawing heavily from his incredible 1977 Nobel lecture, Electrons in Glass.
Ah, so straight from the source material. And our mission for this deep dive is basically to take you from that fundamental, almost childlike question about why glass is clear, all the way into the complex world of how electrons behave in these disordered structures. We'll explore the groundbreaking theories that emerge, like, localized electron states and this thing called the mobility edge, and then connect them to the profound practical applications that sprang from understanding this, well, frankly, bizarre behavior underpinning technologies we use every single day.
And our primary source is Mott's own words, a direct account from one of the leading figures who truly revolutionized our understanding of these materials. It's like getting the story straight from the person who wrote many of the chapters, so to speak.
Perfect. So let's go back to that initial mystery. Why is glass transparent? Before Mott's work, the scientific explanation was anything but straightforward, even though it feels intuitive.
Well, what's truly fascinating here is that the very concept of a band gap, which explains transparency in solid-state physics, it was built on the idea of highly ordered crystals.
Right, like perfect grids.
Yeah, exactly.
Yeah.
Imagine a crystal as a perfectly organized city with electrons moving along predictable gridded streets. In the 1930s, pioneers like Bloch, Peierls, and H. Wilson established that transparency meant there was an energy band gap
Okay.
between where electrons normally reside, the valence band, and where they could move freely and conduct electricity, the conduction band.
Got it.
Visible light, the quanta of visible light, simply didn't have enough energy to make electrons jump this gap.
So the light just passes through.
Right. But crucially, this entire theory relied on the assumption of a perfect repeating crystal lattice, where electron waves would interact with atoms in a very specific way, like Bragg reflection.
Okay, so order was key.
Order was absolutely fundamental to the theory. Glass, by its very nature, is fundamentally disordered, more like a winding forest path than that city grid.
Yeah.
So the big question was, how can a theory based on order explain something so clear, yet so inherently messy?
And what's truly surprising, according to Mott, is that this fundamental contradiction, a theory for crystals, explaining an amorphous material like glass, it went largely unaddressed for so long.
Yeah, it's strange, isn't it?
It was just accepted like a scientific shrug without a deeper look into the why. It's like using a perfectly detailed city map to navigate that winding forest trail and being surprised when it somehow works, but never asking how it works.
That's a great analogy.
So the mystery deepens. But here's where it gets really interesting and a little counterintuitive. Our sources point to a major turning point, not from studying clear, transparent glass, but from black glass.
Exactly, black glass. The initial breakthroughs came from the Leningrad School, led by Kolomiets, starting back in the 1950s.
Okay.
They weren't focused on everyday clear glass, but rather on what are called glassy semiconductors. Yeah. Black glasses containing elements like arsenic and tellurium. Now, these materials had a smaller band gap, but it was in the infrared spectrum.
Okay, so lower energy gap.
Right. Meaning visible light could excite electrons across it, causing them to absorb that light and, well, appear black.
Makes sense.
Their key discovery, really key, was that the concepts of valence and conduction bands could actually be applied to these glasses.
Even though they were disordered.
Even though they were disordered. And even more remarkably, the size of that band gap, and thus the material's conductivity, did not depend sensitively on its exact chemical composition.
Whoa, okay. That's a huge contrast with something like silicon technology, isn't it?
Huge.
In crystalline silicon, if you add even a tiny, tiny amount of an impurity like phosphorus, you drastically change its electrical properties. That's doping. It's incredibly sensitive.
That's the basis of the whole semiconductor industry, really.
Right, but you're saying in these black glasses, you could vary the recipe quite a bit, and the electrical behavior remain largely the same. That's incredible for manufacturing.
It is. If we connect this to the bigger picture, this uh, insensitivity to composition in glasses is a stark contrast to how we manipulate materials like silicon for electronics, where precise control over impurities is absolutely everything.
Yeah.
It suggests a fundamental difference in how electrons behave in these disordered structures.
So what was the reason?
Well, the proposed chemical reason, as Mott explains it, is that when a glass cools from a melt, each atom tends to achieve its right number of neighbors.
Yeah. Okay.
It sort of satisfies its bonding requirements locally. It effectively takes up all its available electrons in strong chemical bonds. It's like the atoms are self-correcting, you know.
Self-healing almost.
In a way, yes. This is very different from the precise, rigid lattice requirements of a crystal, where an impurity often leaves loosely bound electrons that can then conduct electricity.
Right.
This self-healing or self-satisfying bonding in amorphous materials is a radical departure. It suggests an inherent resilience in how they structure themselves.
Okay, so if the standard band theory for perfect crystals wasn't really sufficient to explain electron behavior in these amorphous, messy materials, a critical question emerged. What is the actual nature of the conduction band in glasses? How do electrons really move in these winding, unpredictable paths?
This is where things get really interesting theoretically. Pivotal contributions came in. First, from Ioffe and Regel, who proposed a crucial idea: an electron's mean free path.
How far it travels.
Yeah, essentially how far it can travel without bumping into something. It simply couldn't be shorter than its own quantum wavelength.
Okay, that makes physical sense.
Think of it like a car needing a certain amount of clear road to truly accelerate. If it's constantly hitting potholes, it just gets stuck, right?
Right.
Then P.W. Anderson's Nobel-winning work in 1958 titled Absence of Diffusion in Certain Random Lattices provided the mathematical proof. He showed that in truly disordered structures, electrons can get completely localized,
Localized, meaning stuck.
essentially trapped in specific atomic regions, unable to move freely throughout the material. The resulting model, which is beautifully illustrated in Figure 1 of our sources, describes the density of states in the conduction band of a non-crystalline material. It posits that at the lowest energy levels within that band, the states are localized.
Okay, the trap.
These are like those quicksand traps for electrons, yeah. As the energy increases, you find a continuous range of these sticky, localized states. But then, above a critical energy, EAC, which we now call the mobility edge,
The mobility edge.
the states suddenly become non-localized or extended, allowing electrons to move much more freely, more like they would in a traditional conductor.
So you're saying it's not a gradual speed up for electrons as they get more energy. It's like a switch.
It's a qualitative shift, exactly. Imagine navigating that winding path. Some parts are really sticky, trapping the localized states.
Yeah.
But then you hit a certain point, the mobility edge, and suddenly, boom, you're on a superhighway.
That's a fundamental change in behavior, a real threshold.
Precisely. And this model elegantly explains electron transport, as shown in Figure 2. At low temperatures, charge transport occurs by hopping from one localized state to another.
Hopping, like jumping between traps.
Exactly. This requires a small activation energy, almost like giving the electron a little nudge over a small barrier to get to the next trap.
Okay.
But at higher temperatures, electrons gain enough thermal energy to be excited all the way up to that mobility edge at A, and then they can truly move freely, behaving more like they would in a conventional conductor.
Right. They reached the superhighway.
You reach the superhighway. However, actually calculating the exact position of this mobility edge in complex, continuous random networks like, say, silicon dioxide, SiO2, well, that remains a significant challenge for theoreticians even now.
So experiments are key.
Absolutely crucial. Experimental verification is where the rubber meets the road.
This concept of a mobility edge really changes how we think about conductivity. But what if we could actually control the number of available electrons in a material? Could we, like, flip a material from a conductor to an insulator just by tweaking the electron count?
Now you're getting to the Anderson transition.
Okay.
This leads us to the fascinating concept of a metal-insulator transition. And that's where the Fermi glass concept comes in, as depicted in Figure 3.
Fermi glass.
Yeah. So in any material, electrons fill up available energy states from the bottom, like water filling a cup. The surface of that electron sea is called the Fermi energy, or EF.
Okay, the top level.
Right. In a traditional metal, electrons at the Fermi energy are in those extended states, free to move. But in a Fermi glass, even though there are electrons at the Fermi energy, they are in those localized states we just talked about.
So they're at the top level, but they're stuck in the traps.
Exactly. They're essentially stuck. So the material, while it might show some metallic-like properties, like its specific heat maybe, it acts like an insulator at very low temperatures because those crucial electrons at the Fermi level can't carry current effectively.
I see.
This fundamental change in conductivity that occurs when the Fermi energy, EF, crosses the mobility edge, immediately, is what Mott named the Anderson transition.
After P.W. Anderson's work.
Precisely.
And you can see this progression of conductivity illustrated in Figure 4, which plots log resistivity against reciprocal temperature. It shows different regimes.
That's right. If you have a high density of electrons, so EF is well above EP, the material behaves like a liquid metal. Yeah. Its conductivity is almost independent of temperature. The electrons are largely free, maybe like cars moving in sparse traffic. Siemens theory covers this.
Okay, pretty standard metal behavior.
Relatively standard, yes. But as the disorder increases, or the electron density decreases, you push EF closer to ESIC. Eventually, you reach the I-Regal condition we mentioned, where electrons can't even travel their own wavelength without hitting something.
Right.
At this point, the conductivity approaches a very specific minimum value, Siemens. Mott called this the minimum metallic conductivity.
Minimum metallic conductivity. So it's like asking, is there a fundamental limit to how poorly a material can conduct before it stops being a metal altogether?
That's exactly the question. Mott's proposal for this minimum value, Siemens, was initially quite controversial. It sparked a lot of debate.
I bet.
But it's been strongly supported by later numerical and analytical work. It seems to be a real physical limit.
Okay, so what happens if you go below that? If EF drops below ESIC?
Then you're in the Fermi glass regime. The states at the Fermi energy are localized. Now, at high temperatures, electrons can still gain enough thermal energy to be excited up to the mobility edge, ESIC.
Jumping up to the superhighway?
Right, so you still get conduction, but it has this exponential dependence on temperature related to the energy gap, ECEF, but at very low temperatures.
It can't make the jump.
Flipping is very difficult. Instead, conduction transitions to thermally activated hopping. Electrons literally jump from one trap state to another nearby trap state, needing a little bit of heat energy, KT, to make each hop.
The trap-to-trap jumping.
Exactly. And this follows a very specific mathematical law, conductivity proportional to XBT14, which is characteristic of this variable range hopping.
Wow. So what does this all mean for us? It's like having a dimmer switch for a material's conductivity.
That's a good way to put it.
And it's all about where that electron sea level, the Fermi energy, sits relative to the superhighway entrance, the mobility edge.
Precisely. By controlling the number of electrons, perhaps through chemical composition or an external field, or by controlling the amount of disorder, you can fundamentally change a material's electrical behavior from metallic to insulating.
It's fascinating how such a microscopic aspect of material science translates into such a profound macroscopic difference.
It really is.
This might seem like a lot of abstract physics, but these concepts are far from theoretical curiosities, right? They directly connect to tangible applications and ongoing research that were cutting edge in Mott's time and, frankly, underpin so much of what we use today.
Absolutely. You see systems exhibiting the Anderson transition in materials like the alloy law 1xSXVO3. Here, varying the composition, the X changes the number of electrons in the vanadium D band, literally tuning its conductivity across the transition.
Okay, a real-world example.
But perhaps the most recognizable example for most people is the MOSFET.
Ah, the transistor.
The metal oxide silicon field effect transistor. Figures 5 and 6 in the source show it. This is a crucial device, a cornerstone of modern electronics. Billions of them in your phone, your computer.
Everywhere.
Everywhere. It essentially controls electrical current using an electric field. And at the heart of a MOSFET, there's this tiny inversion layer at the interface between silicon and silicon dioxide.
Right.
Electrons can move in just 2 dimensions there. And by changing the voltage on a gate, you directly adjust the electron density in that layer.
So you're tuning the Fermi level.
You're tuning the Fermi level relative to the mobility edge. You could literally drive an Anderson transition right there in that 2D layer, turning the device on or off.
Wow.
Disorder in that system arises from, random charges trapped within the silicon dioxide layer, imperfections at the interface. But the fundamental physics predicted by Mott still holds true. Experiments by Pepper and others strongly confirm the predictions, including the existence of that minimum metallic conductivity, Siemens, even in these 2-dimensional systems.
Amazing. And you also mentioned amorphous silicon and germanium.
Right. In those materials, defects like dangling bonds, Think of an atom in the network that hasn't made all its required bonds, like a sort of broken hand reaching out, visualized in Figure 7. These create deep levels or states within the gap.
More traps.
More traps, exactly. And these allow for hopping conduction, especially if the Fermi level sits among them.
Okay.
Mott also highlighted two new and really significant discoveries as of his 1977 lecture that truly changed the game for amorphous materials.
What were they?
First, the ability to dope deposited films. This was huge, thanks to Speer and coworkers. For decades, it was thought you couldn't effectively dope amorphous materials like you could crystals. They just seemed to soak up the extra electrons into bonds.
Because of that self-correcting nature.
Exactly. But Speer found that by co-depositing phosphorus hydride, pH3 with selenium SH4, under the right conditions, they could introduce phosphorus impurities that did reliably change the conductivity of amorphous silicon films, make it N-type.
They cracked it.
They cracked it. This was a monumental breakthrough. It allowed for the creation of cheap PN junctions in amorphous silicon.
Which you need for diodes, transistors,
solar cells, flat panel displays. It made amorphous semiconductors truly practical for the first time, a massive enabler.
Okay, that's huge. What was the second discovery?
The second groundbreaking idea was the negative Hubbard U concept.
Negative Hubbard U. What does that mean?
Okay, this one's a bit mind-bending, but incredibly important. Developed by Anderson, Street, Mott, Kastner, Adler, Fritschuk. Quite a team.
Right.
Usually electrons repel each other when they're on the same atom. That electrostatic repulsion energy is called the Hubbard U, and it's positive, U0.
Like charges repel. Makes sense.
Right. But in certain disordered glasses, particularly those containing atoms with lone pair orbitals, think of atoms like selenium or tellurium, having extra unbonded electron pairs defects, like those dangling bonds again, actually prefer to hold either two electrons, becoming negatively charged, or none at all, becoming positively charged, rather than just one unpaired electron, which would be neutral but have a spin.
Wait, so they'd rather be charged than neutral with one electron. Why?
Because the energy gained by the atom rearranging its local environment, distorting slightly and forming stronger bonds when it gains or loses that second electron, actually overcomes the usual electron repulsion. The lattice relaxation energy is larger than U.
So the distortion pays back more energy than the repulsion costs?
Exactly. It stabilizes these charge centers, these valence alternating pairs, D plus and D states. It means the effective U becomes negative.
Wow.
This elegantly explains several key observations about these chalcogenide glasses. Why they often don't have many free unpaired electrons, which would show up in spin resonance experiments, why their Fermi energy seems pinned, stuck in the middle of the gap, and it reinforces that Colmidit's principle about glasses striving for complete bonds, even with imperfections.
That's a really subtle but powerful idea, overcoming electron repulsion through local distortions.
It was a major insight into the defect physics of these materials.
It's truly amazing to think that some of these technologies were already impacting millions of lives and powering multi-billion-dollar industries, even as the theoretical understanding was still, unfolding in the labs.
Indeed. Mott pointed to two old, even in 1977, yet groundbreaking applications. One was the use of amorphous selenium in Xerox copiers.
Ah, the photocopier.
A multi-billion-dollar industry that grew largely before the underlying physics of charge transport in amorphous selenium was fully worked out.
That's incredible. Engineering leapfrogging the science.
It often happens. Think about that office copier. It relies on amorphous selenium's photoconductivity to transfer images. Later, scientists at Xerox themselves, like Schur and Montrol, dug deep into the physics, discovering things like dispersive transport.
Dispersive transport.
Yeah, it means that electrons don't all travel at the same speed when moving through the material after being created by light. Some are faster, some get trapped and released, so the packet of charge spreads out or disperses. Understanding this was absolutely key to preventing blurry copies and refining image quality over time.
Ah, okay. So the science caught up and helped improve the tech.
Exactly. The other example was the Obzhinsky threshold switch, invented by the remarkable Stanford Obzhinsky. Figure 8 illustrates it.
Right, the SWID.
Basically, a thin film of chalcogenide glass sandwiched between two electrodes. You apply a voltage, and above a certain threshold, it suddenly switches from a high-resistance off state to a low-resistance on state. Highly conducting.
Like flicking a switch.
Very much so. And then it switches off again when the current drops below a certain holding value. It's like a solid-state electrical switch.
So what was the debate there?
Well, the initial controversy was whether it was just a simple thermal effect. Does the material just get hot in a narrow channel, and higher temperature means higher conductivity, a thermal runaway.
Seems plausible.
It does. But Mott proposed an electronic mechanism he called double injection,
Double injection.
where holes, or missing electrons, were injected from the positive electrode and electrons from the negative electrode into the glass. These injected carriers meet in the middle, fill up traps, and eventually create a highly conducting plasma-like channel.
Ah, an electronic explanation, not thermal.
Right. And crucial experimental evidence later strongly supported a non-thermal explanation. For instance, measurements show the conducting channel wasn't actually getting significantly hot. And perhaps more tellingly, as you increase the total current through the switch in the on-end state, the current density in the channel stayed roughly constant. The channel simply got wider.
Ah, okay, that doesn't sound like simple heating.
Doesn't really fit the thermal picture, no. Mott believed the conducting channel had similarities to something observed in crystalline germanium called electron hole droplets. Tiny, highly conductive pockets where electrons and holes condense together, like a metallic liquid.
So a quantum condensed phase?
Potentially.
Yeah.
He argued that in this state, both the electron and hole quasi-Fermi energies were above their respective mobility edges, creating a metallic-like state, which could explain the observed carrier mobilities in the on-end state.
These inventions, like the Xerox machine and the Ovchinsky switch, truly represent incredible feats of engineering that, often preceded the full theoretical grasp.
Absolutely.
It really highlights how empirical discovery can drive science forward and how much there is still to uncover, even in seemingly established fields. It just shows you that sometimes the engineers lead the way, leaving scientists like Mott to catch up and unlock the deeper how and why.
And even Mott admitted in his lecture that the full details of the Ovchinsky switch weren't completely settled then. Science is always ongoing.
So we've journeyed through the microscopic world of electrons in glass, seen how a fundamental, almost everyday question led to these groundbreaking theories like the mobility edge and the Anderson transition, and how these ideas now underpin everything from solar cells to the devices literally in your pocket. It's really a testament to the power of pure scientific curiosity and just persistent inquiry.
It really is. This deep dive into Mott's work shows us that even in materials we've used for millennia, like glass, there's layers upon layers of sophisticated physics waiting to be uncovered.
Yeah.
And his unique contribution as a bridge builder, constantly connecting theoretical predictions with experimental evidence, was just immense. His Nobel Prize truly elevated the entire field of amorphous materials, gave it the recognition it deserved,
Definitely.
and the intersection of disorder and quantum mechanics. It continues to offer profound insights and, frankly, plenty of challenges for future discovery. There's still lots to figure out.
So the next time you look through a window or tap on your phone screen or even notice a black, non-reflective surface on some gadget, maybe you'll see more than just transparency or opacity. You might see a Fermi glass at work or electrons hopping across localized states or maybe even a tiny Anderson transition happening right there. It truly makes you wonder, what other everyday mysteries are just waiting out there for their own Mott moment of profound scientific discovery?